Hello, class. This will be the last section of chapter 8, again, talking about confidence intervals. And we're going to introduce a new distribution as well called a chi distribution for this calculation. And to be honest with you, the chi distribution is important because we're going to be using it in some other calculations like goodness of fit and dependence test. This test is very specific, but it's a good way to introduce this new distribution. So decided to go over this section as well. So this is a confidence interval now. Instead around the mean, it's around the standard deviation. And if you do have an understanding of what the central limit theorem states, central limit theorem states that any distribution, the mean of that distribution will model a normal distribution if that's the test statistic that we're trying to evaluate. Guess what? Standard deviation doesn't follow that. So there's a real strict criteria that when you do this, let's see, when you do this calculation, that I couldn't find the right slide, sorry. So let me just tell you. So when you do this calculation, the distribution must be normal or it won't work. So you're going to be given data and it's going to say it fits a normal distribution. And then you say, okay, now I can do it. If you don't know, then you can't do this test. It has to fit a normal distribution because the confidence intervals all depend on that normal distribution idea. And you'll see that, again, we're going to be doing plus or minus the error values like we've had throughout all this chapter. But the more complexity we're going to add is we're going to introduce this idea called a chi-square distribution. And what's interesting about this chi-square distribution is that you can use this to do some testing. And it's set up similar to the t distribution, except it is more skewed aspect of it. And as the degrees of freedom get bigger, meaning your sample size gets bigger, it looks more and more and more like a normal distribution. But when the values are small, then it looks very skewed where the peak is really close to the left side with regards to that. And you can see that in these graphs where the red one has a degree of freedom of 5, but when you go to this black one of 30, it looks degrees of freedom of 30, you can see that that looks very similar to a normal distribution. So a couple of things about a chi distribution. It's not symmetric. Yeah, so it's not symmetric. That is super important to understand. So we don't have these z-scores where +1 and -1 around the means, et cetera. And again, it's really important to realize that the area underneath any one of these distributions always equals the number 1. Symmetric or not symmetric, it doesn't matter. That is always true. And so you're always going to get a value above 0 when we do this calculation as well. And what's interesting here is when we were doing the z-scores, right, they were symmetric. So when we did the 95% confidence, right, we got a z-score of 1.96 minus 1.96. So we could do the plus or minus, right? And we didn't have to worry about that aspect because it's not symmetric. I don't know, I'll say it again, because it's not symmetric, you need to get 2 separate values. And the low end and the high end aren't going to be the symmetric. They're not going to be plus or minus from one another. They're both going to be positive. And so you need 2 numbers. And you find that error with 2 separate numbers in this case. And you'll see that in the example. And so how do you find these crazy z-scores, but now they're called chi-scores, I guess we could call them? You have to look them up in the table. And so the book has table, it's table A.4. And here you have the degrees of freedom, and here you have the tails. And so remember, we're going to have the tails. So one tail would be at the low end, and then this tail is going to be a big one. And so if you look at this, you could see that the upper end is going to be the 90, 95, 97, et cetera. And the lower end, so this would be the 0.025%. So what this is highlighted here is a 95% confidence, right? So the areas between the two are going to be 0.025 and 0.025. So again, if you think about this idea of less than, the lower one, less than, would be 0.025. And then this upper one is going to be 95 plus 0.025, which gives you 0.975. And so you have to read these right off the chart. I did upload a chart to our Canvas account. And let me pull that up for you. And let me put it on the right screen. And so it looks like this. And so you're going to get two numbers here. The high number you'll add and the low number you'll subtract to find the 2 points for the confidence level. Okay. So we have a couple calculations, and here it is that you need to calculate the variance. And the idea here is that you multiply that by the degrees of freedom, which ends up being the n-1. And then you divide now by the chi-squared numbers. And then you have the low end on the left and the high end on the right. And so these formulas are kind of weird, right? Look at them. And then what is standard deviation? It's always the square root of variance. So that's what we have done here. So if the standard deviation is calculated, and then these would be those two extremes. So my plan is to walk through one example here in the slide, and then show you how to do it with an Alex problem, where we can download the information to the spreadsheet and walk through all the calculations that way. So we'll do two of them. The first one we're going to do is the calculation on the slides. So I'm just going to kind of walk you through that. And so the idea here is that you would take these numbers, which we have 7 of them. And first of all, you have to calculate the variance calculation that we have here. And you could see it would be the variance up here, and then you divide by n-1, just like you do sample standard deviation, right? And you see you would get a number almost 2,700. And so now we have degrees of freedom of 6. So where did these two numbers come from? Well, we have a confidence level of 95%. So the high number is going to be 0.975. And then the low number for the area is going to be 0.025. And so where did those numbers come from? Let me pull up the table. So we have the degrees of freedom of 6. So that would be 6 down. And if you go 0.95, there's the low number, 1.234 or 237, excuse me. And then if you go to the 0.025, you'll see that number is almost 14.5, right? 14.449. And that's where these two numbers came from. So now what? Well, just plug and chug a little bit. So the idea is that you plug these numbers in. And so the lower bound for the deviation is going to be 1121.129, right? And so we divide by the 14, that's the big number. And then you divide by the small number, that's going to be your upper bound. And you see that ends up being 13,095. So for a 95% confidence level, you would have the variance between 1121 and 13,095. Pretty big variation, right? And so how do you get the standard deviation? Usually at the end, you just take the square root, right? And so at the end, you would take the square root of both those numbers, and you would see now you get 33.48 and 114.44. So let's go back. And so here is our variance, right? 2699 and some change. So if you took the square root of that, you would get our standard deviation, which is almost 52 and ends up being 51.96. So if I pull up the whiteboard here, first time in this lecture, right? So our extremes are 33.48 at the bottom, and then it would be less than standard deviation and less than 114.44. But what was the value that we calculated from our sample? The standard deviation was 51.96. And here's what's a little weird, right? Is all the calculations that we've done so far, the two extremes were always symmetric, right? And here's another thing, right? The chi-square distribution is not symmetric. So the number in the middle isn't, or the number between the less thans aren't exactly in the middle. And depending on the degrees of freedom and things like that, not things like that, depending on the degrees of freedom, as n gets bigger, the number is going to get closer and closer to being in the center. And so with a number of just 7 samples, you would see that the number isn't very close to the center. I always find that interesting. Probably. All right, and so that's the calculations that we did. And so this just talks about the justification method here. And so this is super important. That was the slide I was looking for at the beginning. The method in this section only applies if the data is a normal distribution. And most of the time you don't know unless you have to do an analysis or you have a lot of data. And so you can see what's going on, which is nice as well. So what I'm going to do now, I'm going to pause real quick and pull up Alex, and that takes a few minutes. So what I decided, I'm going to do a separate lecture and do an Alex example on section 8.4 using Excel. So I'm going to end this recorded lecture, and there'll be one more walking through a detailed example using the spreadsheet.